Hi, everyone. Welcome and thank you for joining today's webinar, Particle Classroom Series 3, Refractive Index and Laser Diffraction. My name is Julie Chen Nguyen, and I'm going to be your host today. So let me introduce you, our speaker, Dr. Jeff Bodycomb. Dr. Bodycomb is our product line manager for particle characterization. He received his PhD in material science and engineering from Rutgers University, and he has experience focusing on dynamic light scattering, laser diffraction, and image analysis. He's especially interested in sources of error in measurement, scattering techniques, and microscopy. As you know probably already, that Jeff is also the master of all bad but witty jokes. Sometimes I get it, but most times I don't. All right, Jeff, I'm going to pass the ball to you. Please go ahead and share your screen.
Well, Julie, thank you for the introduction. I feel like with the introduction like that, I need to tell a joke, and then you can decide that they're both. Well, you'll realize why I picked my chosen profession anyway. So a mushroom walks into a bar and asks for a drink. The bartender says no, and the mushroom says, "Why not? I'm a fun guy." And so anyway, now everybody knows why I'm in particle analysis. Back to the matter at hand. Yeah. So today I'm going to talk about refractive index and laser diffraction. So really, when you start working with laser diffraction, you're going to hear about this refractive index concept, and then you're going to need to know what to do with it. And I'd like to review all that and cover some ways to think about it or to get the right number into your instrument and get better data for yourself. So first, what do we mean by refractive index? And kind of back up, you realize that you have particles, and in most cases, and in every case where laser diffraction works, the optical properties of the particle are different from those of the surrounding medium. And if that's not true, you won't have any scattering, and that means you have no signal to work with. So if I draw a wave coming from left to right of light, going through the particle, you can see that the amplitude is going down as the wave travels through the particle due to absorption. And you'll see the wavelength gets shorter inside of the particle because of the change in refractive index of the particle, or change in material properties. I'll go into a little bit more, but wavelength changes are generally described by a real component, and intensity changes are described by an imaginary component. The real and imaginary comes out because the equations for light are kind of best manipulated using complex numbers, which kind of tells you what a mess they are, that I have to go and use imaginary numbers to make it work more easily. It can be kind of a headache. So why do I worry about refractive index? So really, light scattering is optical measurement. And so you really want to include the behavior of light inside the particulate material as you think about light traveling through your sample and suspending medium. So under certain conditions, and they're fairly common, you have to include that behavior to get the right answer out at the end. If the particles are quite large, over about 25, 26 microns, you could use a simplification called Fraunhofer diffraction to describe scattering as a function of particle size, and refractive index is less important. When particle diameter is about the same size as the wavelength of light that you use for the measurement, you really desperately need to use what's called Mie scattering theory to make your calculations. These calculations are much messier. They include what happens to the light inside the particle, and so it's more accurate. And refractive index is going to tell us what the light's doing inside the particle. So quick comment on Mie versus Fraunhofer. In Fraunhofer, which is kind of shown by the disk at the lower part of the slide, we really treat the particle as a two-dimensional disk object. And so it's just a flat thing. Mie not only includes the behavior of light inside the particle, it does it because there is an inside to talk about, because they treat the particle as a sphere. And so with modern computers, there's really not a lot of good reasons to pretend that the world is two-dimensional and that you don't need refractive index. I kind of go through Fraunhofer because it's a nice exercise to understand scattering, because I can wrap my head around it. But for calculations, I use Mie because my computer can handle it, and I get more accurate results, and it works for everything that I deal with. So here's another example or difference between the Fraunhofer Approximation results, which describes scattering, and next slide will be Mie scattering calculations. So I have a scattering angle on the kind of left side, particle size, going across the bottom right, and energy or scattered intensity going up. And you see that it's a very smooth curve where you have your peak and your scattering intensity shifting steadily with particle size, not a whole lot else going on. Well, if I go and do some calculations using Mie theory, which is more accurate, and here I tell you what parameters I use for the calculation. My liquid refractive index of 1.33, which is water. A refractive index of the particle 1.6 and no absorption. Now we see the same graph, scatter angle, particle size, and energy, and it starts off all lumpy and mountainous with peaks at some sizes and valleys at other sizes. And then eventually, for the larger particle sizes off to the back right, it smooths out to look like that Fraunhofer result you saw earlier. So all this extra information we really need to properly analyze these results from these smaller size particles. Okay, so that's nice in theory. What happened in practice? Well, let's look at something like a glass bead. And glass beads get used in all sorts of things, from larger sizes, which would be reflection for road markers, down to very, very small silica beads, which are used for semiconductor manufacture and polishing. And here's an example of a standard, and it's about 15 microns. It's at 13.5 microns. The red peak is what happens when I calculate with Mie scattering. I get the right size result. So the left, I have differential size distribution as a function of particle diameter on the bottom. If I went and calculated that data with the Fraunhofer, I'm going to see two peaks in my size distribution, one at about 3 microns and one at about 20 microns. And my D50 is about 3.6 microns. So what's happening is that when you measure glass beads, because they're clear, the light's going to kind of knock around, have some internal reflections, and then come out, and you'll get extra peaks and scattering. Fraunhofer doesn't capture any of that kind of behavior. And so it just thinks there's multiple peaks, there must be multiple sizes. Whereas if you use the Mie calculations, you know that there'll be multiple peaks for this size of glass beads. So anyway, there's one justification for worrying about all this. Moving down in size, let's look at CMP slurries, where the red is, again, the calculation with Mie scattering, differential size distribution as a function of particle diameter. And we get basically the right answer, which is 100, let's call it 150 nanometers or so. But if I use the Fraunhofer, I'm going to get 1, 2, 3, about 4 microns. Okay, again, what we're basically doing is, because these particles are in that kind of the irritating size range where the behavior of light inside the particle matters, then our scatter intensity behavior changes. And so if we ignore the fact we have a three-dimensional particle and ignore the refractive index, we're going to come up with the wrong particle size. And basically the difference between 150 nanometers and to 4 microns for particle size is the difference between making a decent semiconductor wafer and making basically a pile of expensive sand. So this is really a huge difference in practical application of laser diffraction for monitoring particle size. Right now, if you have 3 micron chunks in your CMP slurry, you wouldn't be manufacturing very much. So I made a quick reference in the introduction. So we like to talk about refractive indexes having two components, a real number n and an imaginary component k. And the real component is the ratio of velocity of light in a vacuum to the velocity of light in the material. And quite often that's when you look in physics textbook and you look up refractive index, that's the number you will get. I is the square root of -1, and k is the extinction coefficient of the material. So for example, if you have soda lime glass, refractive index of 1.5, it's clear, so there's no significant absorption, assuming it's very pure. Yes, the light travels about 67% of its speed in vacuum, and so it gives me a refractive index of 1.5. You've probably seen pencils bend when you put them into a glass of water, or they look like they bend. And basically what's happening is, if you look on the right side, if I bring in some light from medium with refractive index n to a medium with refractive index n prime, the light will bend, travel through this medium and bend again on its way out. So things will tend to appear offset when it goes through this change in refractive index. These angles, theta and theta prime, can be related to each other through the refractive index, and you can use Snell's law, n sine theta equal n prime sine theta prime. And you'll use that when you're developing certain kinds of refractometers, where you just look at the bending of light that goes through the sample. Now, if you have a very high real refractive index, that's going to start pushing you towards where you can simplify your math to Fraunhofer if you really want to go in that direction, because really the determined particle size becomes a weaker function of total refractive index. The imaginary component is really the extinction coefficient of the material, and it's a reduction in the scatter in transmission of energy because of absorption and scattering of light, although really I should emphasize absorption in this slide. So K is the extinction coefficient, lambda is the wavelength of light, alpha the absorption coefficient. You will also see alpha reported for some materials, and 4 pi is our friends from circles. The absorption coefficient alpha is the reciprocal of the distance light will penetrate the surface and go to 1 over E of its original intensity, about 37%. Opaque materials have very high extinction coefficients. All the light gets absorbed, nothing makes it to the other side, the material looks opaque. So if we were to plot intensity of the light as it travels through the material, that's on the bottom, I start at 100% when it enters, and at some distance d, my intensity is down to 37% of where it started, and so 1 over d will give me alpha. K is lambda by 4 pi alpha, so for K of equal 0.41, you solve for alpha, eventually you'll find out that d is about half a micron. So how to kind of sum all this up? And that goes back to that original circle with wavy line in the first slide. So the circle is your particle. The red and blue are the electric field of the light that's traveling through your system. And you see a peak-to-peak distance out here that's quite broad. And then when it hits the particle, that distance becomes quite short. And that's because of a high real refractive index of 2. And you can also see that the amplitude is steadily decreasing, and that's due to the extinction coefficient 0.05. When it exits the particle, my amplitude is now quite low, and my peak-to-peak distance has gone back to its original value here. So going from air into a particle and back out. Now, this light inside the particle is going to also be reflected and may come out at different angles. And so we know these intensities as we go to calculate the details of the scattering. All that's captured in the math and all that's captured in the computer. So generally you have to get the right number in and press the button. But knowing where the number comes from and what it's doing helps you press the button with the right number. A little bit of bad news for particle analysis. It's not as bad as you think at first, but we'll address it. Refractive index is wavelength dependent. And the dependence can be described by a number of equations. One's the Sellmeier equation given at the bottom. I won't read it for you because it's long and boring, and the slides will be available online if you wish to copy them later. And modern instruments tend to have multiple light sources, generally with 2 different wavelengths, and they do that because we're interested in accessing a broader range of particle sizes. So you use short wavelengths for smaller particles. So, okay, great. I have a red for big ones, a blue for small ones, great instrument. Well, wait a minute. What about this Sellmeier equation? Well, refractive index varies with wavelength. Does that mean I get different results off the red and blue? It's possible, and modern software will certainly allow you to type in different values for refractive index at each wavelength. But as in this case of BK7 glass, that difference is not very significant. It's between 1.53 and 1.51. So it's a relatively small difference in real refractive index. And generally, you're going to have other experimental issues that will swamp these sorts of considerations. One place where it could matter is something with a lot of interesting optical behavior and the right particle size. So you're thinking submicron pigments. Pigments, of course, are exciting because you use them for color, and that means they have interesting optical behavior. So that's one thing to check, but most of the time, you can cheerfully go through life ignoring the variation with wavelength. So what happens as I vary refractive index to my scattering. So this is kind of a first way of looking at what's going to happen as I type in different numbers and what's the math going to do. The left, I plot scatter intensity. The bottom is scattering angle. And then I have different refractive index values. So the blue is 2.5, no absorption. Black, 0.01 I. Green, 0.1 I. Red, 1 I. So as the imaginary term increases, the location of this first peak shifts to smaller angles. Now, if you are using Fraunhofer or ignoring this, you say, well, smaller angles means larger particles. Or if you listen to my diffraction talks, I mentioned the same thing. Once you recognize that there's an absorption term, then your interpretation becomes a little bit more subtle. So that's the first thing to notice. More importantly, though, is notice my choices of values, 0.01, 0.11. The change in scattering with imaginary component is a fairly weak function of that absorption. And so you're really kind of trying to pick the right decade for absorption rather than trying to get to the last value, to the last 2%. If I look at the real term, so this is all no absorption. The black is 2.5. I'm sorry, black is 2.51, blue is 2.5. So a small change in real refractive index does almost nothing to the scattering curves. If I jump from 2.5 to 2.6, I can see a big jump, and then from 2.6 to 2.7, I have a small jump on that first order peak. On higher order peaks, you see some bigger differences. So the real term, the results depend. I have some data shown later on, which will guide you how to look at sensitivity of these. So you do have to pay attention to the real term and dial it into as tightly as you can. Okay, well, we're not too interested in a physics discussion if we can get away with avoiding it. So let's get some rules going. For your imaginary component, if you have a truly transparent material, then just use 0. If you have slightly opaque materials, use 0.01 or 0.1. And for opaque materials, use a value of 1.0 or higher. Now, values can exceed 1, for example, and there's a website here, byu.edu, with copper, an extinction coefficient of 2. So you can go quite high on the imaginary components. So refractive index effects are most pronounced when the particle is spherical, transparent, the refractive index of the particle is close to the refractive index of the fluid, and particle size is close to the wavelength of the light source. If you have non-spherical particles or opaque particles, or very high refractive index, or very large particle sizes, the refractive index effects become less pronounced. Okay, quick aside here. You may be working off of some older instruments and older methods, and you may stumble across the relative refractive index. So for these older instruments, in order to simplify some calculations, people used to just look at the ratio of the real to the imaginary, refractive index of the particle by the refractive index of the medium. So if I had a particle with a refractive index of 1.6 and a liquid refractive index of 1.33, I'd divide the two and get a relative refractive index of 1.203. And then you would have a kernel term. Sometimes you have a kernel term separately, sometimes you don't, depending on the instrument. If the extinction term would be 0 for transparent, and you have a kernel function that looks something like this, 1.20 minus 0.000 RRI. So if you see something with RRI, it could be relative refractive index. And if you're transferring a method, all you need to do is undo the math to find the refractive index of the particle for typing into modern systems. Now, if the material was somewhat opaque, you would see the extinction go up, and so it'd be 120 minus 0.20 RRI. Kind of the take home here is if you stumble across relative refractive index, you're going to have to back calculate from modern instruments. If you look at cement, and so let's see some more practical examples of varying refractive index. I'm going to affix the absorbance on the right and vary the real refractive index. And the box got shifted a little bit. It should be on 1.6 is the right answer. The upside down triangles right here. So this is volume less than, so this is a cumulative plot as a function of diameter. And you can see that there isn't a whole lot of change in the results for these three choices of real refractive index 1.7, 1.8, 1.9. If you look at very large changes, you'll see a jump in your measured particle size. I'm sorry, this box should be at 1.7. The upside down clear triangle, which is right in the middle of the black boxes you can't see, and the dark triangles and the white triangles. This is quite good. It tells you for this material, which is cement, some variations real refractive index don't change your final size result. If I look at the imaginary refractive index, you see percent less than on the left as a function of measured diameter. Again, you'll see a little variation really at the small, finer particle sizes. I should have the upside down white triangles, which I can't see because they're buried underneath, they're buried right here. So they're well grouped, and you'll see a steady march for the finest particles, but at D50, not much effect. Another practical example, here I show a size distribution as differential for starch. If I pick a refractive index of -0.1, which is fairly reasonable for this material, I see two peaks, kind of makes sense to you. If I use a very high imaginary index, -4, I still see roughly the same size distribution with the same peaks. So the first, going back to moderate, about 1.5 micron and 10.8 micron. And here it's still about 1.5 micron for the first peak and about 8 micron for the second peak. If I were to switch to a value of 0 for the imaginary refractive index, you can see my two peaks have kind of collapsed into one, and quite a big jump in the measured size distribution. So you want to be very happy with this result. Okay, so kind of the first couple things to think about as you start thinking about refractive index. First, does refractive index selection matter for your sample? Are you over 25 microns? Probably not a big deal. If you're smaller than that, you're going to start thinking about, are your particles opaque? Just look at them. If you're not clear, use a non-zero imaginary component. If your particles are not spherical, or if they're rough, you would tend to bump up the imaginary component. This is in part because the non-spherical and rough surfaces of the particles tend to absorb some extra light. Very large particles, if you know you're over 20 microns, just pick a high real value and high imaginary component, and you're good. I mentioned about imaginary values before. If they're completely transparent, go with 0. And remember, you can go very large. One game you can play, which I will talk about later in this talk, is determine the real component and then vary the imaginary component and look at your data to minimize the residuals to find the best choice of imaginary component. So finding real refractive index values, there are a couple ways to approach. One would be to use an Abbe refractometer, and if you have a particle sample, you could disperse or dissolve it at different concentrations, plot concentration as a function of refractive index, extrapolate to 100% particles in order to find the effective refractive index of your particle. Much more popular is the Becke line test, and there are service labs that will do this if you don't want to buy the oils yourself. If you have light coming from the bottom of the page into a particle and some oil, the particles act like a lens, and you're going to kind of see some focusing of the light around the edges. So you see a bright center and a dark line. As you move your focus up and down, the position of that dark circle is going to shift in and out of the particle. So as I move my focus up, I'm going to see it move, and the refractive index of the particle is greater than that of the oil, the line should shift in. And if the refractive index is less than that of the oil, the line should shift out. So you can decide whether your oil has too high refractive index or too low a refractive index. And then put your particle in the second oil and try again. Here's a different set of images. Another way to think about this is as you move away from the thin section, raise your objective or lower the stage, the Becke line tends to move into the material with the greater refractive index. So I move up and the particle has a high refractive index, my lines move in, and vice versa if I have a higher refractive index oil. So if you want to do this, then you would need a series of oils with different refractive index values. So Cargill Labs sells a set of refractive index oils, and you can kind of look them up and see how to buy them. So these are some old prices. Just go ahead and warn you, but you're into probably a $400 purchase here to get a set of 31 liquids with different refractive indices, and you would try your particle in each one systematically until you found the oil that most closely matched your particle. Rather than do this and do the lab work, many people will send their particles out to someone like Micron, have them do it once, and then you'll have a value for your material forever, and away you go. Now, before you start down that path, remember that the internet is your friend. I may not be a millennial, but folks tell me that this works quite well, and I agree with them. You can use something like luxpop.com and find your substance, type in your wavelength, temperature if they let you, and they'll give you refractive index values at different wavelengths. Yeah, so a couple of things. One is, please pay attention to the wavelength. Some refractive index values are reported at very high and very low wavelengths because that's relevant to the people doing the work at the time. We're really interested in what's happening at 650 nanometers or at 405 nanometers. Generally, any visible wavelength is probably going to give you a good enough refractive index value for particle analysis. So even more straightforward these days, type in refractive index, magnesium stearate, and you can just kind of look through the Google results. And here, StoChem has a result, says refractive index 1.56. That kind of passes a smell test for organic material. So I'm pretty happy. If I was going to use this value for my work, I would go and see if the same value comes from several sites and check that the wavelength of each worker is close enough to what I want to work out. Okay, I think somebody on registration asked about mixtures, and I was very happy they did because I went and put these slides in, so I didn't feel like it was worthwhile. The refractive index of a mixture is generally estimated as the refractive index of each component times the volume fraction of each component. Okay, we could also rephrase that in terms of density. Yeah, so if I look at the error analysis on the left, chi-squared, as a function of my imaginary component, and then I can see that the error is quite high for zero imaginary, and then as it goes down and drops to minimum, then the green, which is the median size by the LA950, comes quite nicely close to that of what they found by SEM. So the left should be okay, and then there's a similar analysis for a different material. We'll get into what all those plots mean in a few minutes. So going back to these mixtures, I have a 205 minus 4 and 2.35 minus 3 imaginary. Not much real difference in the imaginary components, but difference 2 versus 2.3 on the reals for this particular material. And the red spikes are from SEM, so manual microscopy. And you can see that my median size, 0.64, 0.65, 0.75 by SEM, was reasonably close by volume and by number, all things considered. And I don't see a lot of variation. So I'm probably going to take that value and declare victory. And part of that is that SEM, I'm a little worried about the statistics and how many particles I'm able to count. So I show you those plots and mention these chi-squareds, and I'm going to go into R parameter now as a way of estimating refractive index. So I give you the equation for chi-squared and R. These are two different statistical tests for goodness of fit. Chi-squared is an estimate that depends on expected standard deviation for each detector, and R is just normalized by the number of detectors and the scattered intent and the intensity of the Y values. Generally, we track R parameter, and if I plot intensity as a function of channel number, I can have the actual measurement in blue, theoretical in red. And of course, you want these numbers to match up. And so if you look on the right, you're going to, and our parameter on the left is 6.5 e to the minus 2. On the right is 5.05 e to the minus 2. And you can see there's a little variation between the red and the blue here. And there's a much better overlay out here at these higher angles. So this is two different refractive index values, which of course I didn't note properly here, so I apologize. But this is how I would compare two different measurements to find out, or two different calculations to find out which gives me the better fit. And what I'm really doing is taking advantage of the fact that in scattering, there are multiple scattering peaks. And so as you move further out in angle, if your peaks aren't arranged right, then you say, hey, something's wrong with this data. And that's why you have these misses up here. So if I take a material, I would find the real component by looking it up. Since it's possible to look up or measure the real component, I really like to do that. For the imaginary, first, it's a little bit less critical. I just need the right order of magnitude. And second, it's a little bit harder to get my hands on it. So I say, okay, I know real is 1.57. I've measured 0, 0.1, and 1i. R parameter 0.54, 0.054, 0.036, 0.0535. So this middle one of 1.57 minus 0.1i, which is the blue, is going to be the closest match to the data. And so that's going to give me my estimate for imaginary refractive index. And that's going to work pretty well. So what's going on here is that to make the red and the black lines fit, not all the peaks fit perfectly. And so there's imperfections I can pick up in the R parameters. And because there's those imperfections, I can say, hey, you know what, this blue is the best one, has the best fit to all the peaks. The LA960 software has a method expert where I can go and systematically explore different conditions for measurement, including pump speed, particle concentration, ultrasound, measurement duration, and our friend refractive index. So there's a real and imaginary refractive index wizards. So what I do is I'll start the software up, and I will, go back. I'll press the real refractive index wizard. So I'll fix the imaginary. I'll select the active data. I will type in 1.33 is my liquid. Hey, that's water. 1.5, 1.6, 1.7. So 5 different values of real refractive index. And I'll input 0 as the imaginary component. I'll probably do that if I think the material is actually clear. Otherwise, I'll use 0.01 to start with. Then press execute. It goes off and creates all the kernels, makes all the calculations, and reports to me a nice graph of size distribution for each set of conditions, D10, D50, and D90 for each set of conditions, and the R parameter for each set of conditions. Say, hey, 1.5, the lowest R parameter, looks like the best looking result. I can then select my best value, 1.5, and then apply that to my method. You can also do the same thing to find imaginary component, which like I mentioned before, is something I do much more than looking for real components, because I really can look up or measure refractive index of real components. And so I just prefer to have as much outside data as I can when I go into these measurements. So let's start with some TiO2. I look up the real refractive index for the phase of TiO2. I use the R parameter to find the imaginary. And so I go through that. R parameter is in black. I see a nice dip at 10 to the minus 2i. Here is D10, D50, and D90 for that result. So 2.7 minus 0.01i. I then go through, because I could just kind of see what happens for different choices of refractive index, and try all the values. So on the left, I have the imaginary refractive index, and on the bottom, I have the real refractive index. I have a surface plot where the lowest value for the R parameter is here at 0.1, and the purple regime, 3.2 and 0.1i. So what happens D50? Well, remember up here, I have pretty high R values compared to here. D50, around here, D50 varies strongly. You can see the contour line's quite close, but this is where I think that the right index sits using this analysis, which is kind of where the contour lines are broadly spaced and there's not a big change in D50 with choice of refractive index values. D10, you see a lot more sensitivity refractive index. Why is that? Because that's a smaller, finer size of the particle size range. So somewhere around 200 nanometers. And D90, again, you see tighter contours for these larger particles. It's probably just bad luck. And I plot up the results. I throw in the red, which is the Fraunhofer kernel. And then blue is 2.7, black is 2.6, and green is 3.25. And they'll all come from from 4 different ways of looking at the data. Let's compare them all. So let's start with the correct value. I get the right phase of TiO2, and I do a pretty strict estimate of the imaginary refractive index. And so D10.3, D50 0.42, D90 0.8 microns. Let's pretend I was not so careful in my Google search and I found the wrong phase of TiO2, because there are two phases of TiO2, rutile and anatase. So if you just look up refractive index of TiO2, you might grab the wrong one if you're not reading up carefully, or if you're in a hurry and your boss wants the results yesterday. A lot of good reasons. And I see almost no difference in observed value for D10. D50 have about 7% difference, D90 about 2.5% difference, D90 0.8 microns. Let's say that somebody says, well, just use Fraunhofer because, hey, Fraunhofer doesn't require refractive index and you don't know refractive index. So I go and analyze data using Fraunhofer. Now I'm looking at 30% errors for D10 and D50. So D90 is kind of okay, but this error got really big because I ignored the refractive index value. Now let's back off from Fraunhofer and say I don't want to use Google, and I don't want to go find the right values. Let's just go minimize the R parameter, and let's make those surface plots like I just showed you. Now my error on D10 is about 13%, error on D50 is about 12%, and error on D90 is about 10%. So minimizing the R parameter for the real refractive index is going to get me kind of close to where I need to get. A Google search where I'm not real strict about it, getting me 2.6 instead of 2.7, is going to get me pretty close to where I need to go. At 7%, we can start arguing about sampling error if we wanted, although I discourage it. And Fraunhofer is just going to get me into trouble. So kind of take home here is, this is the way you want to think about it. First, can I get the right number? Second, what literature value is there that's close? Third, let's look at minimizing R parameter for the real refractive index. And I won't even mess around with Fraunhofer. So here's another example. This is 5 micron TiO2 with different real refractive index values. And I plot D10 in blue, D50 in red, D90 in green, imaginary of 10 to the minus 3. So I go back here, I say, hey, diameter doesn't change with refractive index. So why bother? Why not just use Fraunhofer? Well, it turns out the results are quite different. And so red is the calculation using Fraunhofer, and blue is the calculation using Mie, and a pretty decent refractive index value. So you say, well, wait a minute, there's no variation in the size result with refractive index, what's going on? And what's really happening, if you go back and look at this calculated scattering, is that the peaks line up quite differently in Fraunhofer compared to Mie. And that's because we're thinking about a three-dimensional particle instead of a two-dimensional disk. And that matters at 5 microns, more so than it matters at, say, 25 or 50 microns. So there's a few recommendations falling out of this. The first is use the Mie model when evaluating laser diffraction data. Search literature as much as you can to start with. See what other people are using, or measure the values yourself, because that's going to get you a lot closer to the correct answer. If you can't find literature values, use the data to estimate these values. Use the scattering data to estimate values. It's better than guessing or using the Fraunhofer model. And finally, something I don't talk about elsewhere in this presentation is once you pick a refractive index value for your system, stick with it. So let's say you're making TiO2, just for sake of argument, and you're running your process and you're analyzing the effect of different parameters on size distribution. Well, you don't want to go back and be changing the refractive index value and comparing the data between a refractive index value 1.6 and 1.7, because you're not going to know if the jump is because of refractive index value choice or because of process changes. So pick a value carefully and then stick with it so you can more clearly understand what else is happening in your process as particle sizes or measured particle sizes change. A few more things. When you measure a sample, you can always recalculate with different refractive index values and see how important it is. If you, like my case of the 5 micron TiO2, I might get to the end of that calculation and say, you know what? It doesn't matter what value I use, so I'm not going to worry about it anymore. Or if I find out it's quite sensitive, and I will go send the sample out for a vacuum line test. As I mentioned before, make sure you do something preferably outside your scattering measurement to get the real component of refractive index. Recalculating using different imaginary components does work pretty well, particularly if you want to capture the effects of surface roughness. Choose a result that minimizes the R parameter and check if these results make sense. You should have multiple techniques. Certainly a little microscopy, even pinching the sample between your fingers, can help you see if there are any large particles or any other surprises in there. So make sure everything kind of hangs together consistently. Okay, well, I want to thank you for your time and open the floor for questions.
Well, thank you, Jeff, for the excellent webinar. Well, one question that came in during registration, which I think you had briefly mentioned about, specifically is how to choose RI value using the optimization function of HORIBA instrument.
Okay, yes. So I did kind of walk through that. All right, so you're gonna look for a button called the Method Expert. It's gonna open up and you're gonna have a bunch of buttons for different things to optimize. And you're going to pick the real refractive index wizard or the imaginary refractive index wizard. You're going to follow the steps in the wizard. And so in this slide, I kind of walk through the major steps. Which data do you work on? What's your liquid? What real components do you want to check? What imaginary component to use? And then execute. During execute, the software is going to start blinking a bunch because it actually is going through and calculating new kernels for each refractive index test value, and then calculating size distributions for each refractive index test value. And at the end, it's going to spit out all the results for your inspection. So you'll inspect, you'll pick your favorite, and it will give you an option to save that into a condition file, if I remember right. Although most frequently, I just write it down as I go through my condition and then fill it into my condition file manually later on. But that's kind of my own workflow. That's not the only way to do it.
Thank you. And this webinar is going to be recorded and posted on our website too. So go ahead and look for slides 37 through 40 if you want to use the optimization function for HORIBA instruments. And I think this is specifically for the LA960. Is that correct, Jeff?
It's on the LA950 and LA960.
Perfect.
Yeah.
Cool. All right, another question. Early in the presentation, you mentioned a high refractive index of refraction. How do you consider a high RI value?
I'd say anything over 3 would be good. So let's very roughly about twice the refractive index of my medium would be high, and then it's going to be a little bit particle size dependent. Yeah, so let's say you start thinking it's high when you're twice your medium refractive index, and you might do a sensitivity test. Now, let me give you the real intellectually lazy, get through the day approach. Once you know it's high, you type in the value and let the software do the calculations, because the software is going to be pretty cheerful whether you type in a value of 1.4 with liquid 1.33 or refractive index of 3 and liquid of 1.33. So yeah, kind of these estimate methods are falling out of favor, at least in my mind, because you don't need to estimate anymore. You can just have the calculations done for you. So I hope that answers the question and saves you from really having to remember the answer.
Thank you. Okay, so one more question that came in. I had optimized an I in the past.
Okay.
Okay. But found a textbook very different. How do I pick?
Okay, so my first question would be, how different is different? So let's say you optimize to 0.01 and the textbook says 0.015. And then I'd say, you know what? It's less than a factor 10 difference. Just pick one and move on. The other, oh, wow. Okay.
So specifically, this person's looking at 0.01 I versus 1.9 I.
I'd see, okay, so, wow. Okay, so now you really do need to pick. All right, 0.01 versus 1.9 is basically between something that is kind of clear to translucent to something that is black that you can't see through. So looking at the particles might give you a pretty good clue as to which is more accurate. Yeah, and so you may have found kind of a false minima in the optimization, or may not work for your sample as well. So I don't know which is which, but you can look at the sample and tell a difference there, fortunately. Okay,
So
opaque green.
Yes,
Okay,
so this person added basic copper carbonate opaque green.
Okay, great. So is opaque, that says high. That's all good. It's green. So green is going to reflect green, and we don't know what it does with blue and red. Okay, so now, and this is this is a material that's going to have a strong color dependence or wavelength dependence on the refractive index. So I have to go back and see what the book says about 650 nanometer versus 530 nanometer. So versus green versus red. So it could be this is one of those materials where the refractive index is changing quite sharply with wavelength in the visible regime, which is going to be a headache. And you might find out that red light gets through, and the author of the book did the measurement in green or vice versa.
Oh,
So that,
wow.
yeah.
So to
Yeah,
add to
yeah, I
this
saw
person is
that.
measuring some micron sizes just for the rest of our
Yeah.
audience. So we're looking at some micron size particles are green. Um, we're having a hard time optimizing it.
Yeah, I have to. Yeah, that's a case where you want to look at the wavelength dependence of refractive index, or I'm sorry, of imaginary refractive index. And I
So
think
again,
that's clarify everything.
good. And again, we can always, I guess, email labinfo@horiba.com if we have specific data that you wanted us to look at to support your
Yeah.
system.
Actually, for absorption, you could buy a system from HORIBA. We have a Duetta fluorescence and absorbance device. That's quite an investment for one sample, but hey,
You'll get it right.
just thought I'd throw it out there.
Thank you, Jeff. All right. Anything else that you would like to add?
So we just have a moment before, so I'll add the other joke as a bookend. If you're growing fungi, what size room do you need? As much room as
Which is,
possible. You've heard that before, haven't you, Julie?
yeah, because it's a fun.
See,
No
they're
wonder
bookend.
our audience are laughing.
Well, I don't know, they all seem to be dropping out pretty quickly. All right, we should end it here.
Well, for now, have a great day, and we'll see you all next time. Thank you, Jeff.
Thank you very much. Thanks, everybody.
Alrighty,
Bye-bye.
bye.